My project is on mass versus magnets. My name is Ysap and I'm a student at Ysap High School. So here's some background information. A magnetic field is produced by electrical currents. The magnetic field sources are essentially bipolar, meaning that they have a north and they have a south pole. The SI unit for the magnetic field is a Tesla, and a Tesla is equal to 10,000 Gauss. Magnetic poles are points where the magnetic field lines begin and end. These lines will come together at the poles. In this picture, we see both the magnetic and the south pole. We see how their lines of direction are varying opposite to each other, and towards the center where they come together, they forms an ellipse. This would in essence explain why the magnets repel each other. Next, we're going to learn a little bit about some rare earth magnets. These are the magnets that are used during the experiment. They are the strongest permanent type of magnets made from alloys of rare earth metals. Rare earth metals are very brittle, which is why you have to take precaution when using rare earth magnets, because they are capable of breaking. The atoms of rare earth magnets can retain high magnetic compounds in a solid state. High magnetic compounds of an atomic lever in combination with a stable alignment results in high strength, which is why it is important that you keep them aligned. On day 6 of magnetism research in class notes, we learned that the magnets are easily breakable, and once broken, you have a new north and a south pole. Magnetic fields always point to the south. The Earth's magnetic field is similar to that of a bar magnet. The Earth's magnetic pole is really a south magnetic pole, as the north ends of the magnets attract. So, our variables. Through this experiment, the independent variable would be the power of the magnet itself. The dependent variable, which is what I'm changing, is the weight that's being added that will make the magnets repel against each other. Why am I conducting this experiment? I did some research on the bullet train. How? How does it work? How does the bullet train operational in Japan? How is levitation possible? Are magnets really strong enough to transport hundreds of people a day? It seems almost impossible. How strong are magnets? It is understandable that magnets that allow the bullet train to function may have cost hundreds or maybe even thousands. How strong are affordable magnets? From this, the levitation experiment took root. Here's a fascinating picture of the bullet train in Japan that carries thousands of people a day. It seems incredible to even think that something this big and this fast could levitate over magnets. So, how am I going to research and design this experiment? The research collected leads me to reasonably infer that the magnets should be placed facing the opposite direction so that they will repel each other, having both poles that are same towards each other. That way they will repulse. It also leads me to conclude that I should have them directly aligned above each other. Through this, I found out that I should divide my foam board into 4 sections, both diagonally and horizontally, and able to align them correctly at each corner. In these images, you can see how the steps were carried out. First, I cut the foam boards, and to secure them on the sides so that there would be no fringe, I surrounded it with tape. Once that was done, I measured the board and divided it into 4 sections, both horizontally and vertically, marking every corner where I would place the magnet. Based on my research and how I have learned that magnet poles that are the same will never touch, I have hypothesized that the magnets indeed will never touch. Rather, once forced to the test by massive amounts of weight, the magnets will shatter and new poles will be created. Step number 1. The foam board was measured and cut. After that, I added tape to the edges to provide a smooth finish. After this, I made the calculations of how I was to divide the board. The tools used during this step was a foam board, a cutting blade, tape, and a ruler. Step number 2. The board was separated out and the lines were marked on the board. After this, I began to think about the positioning of the magnets. On the same day, I made the holes in the center of the outermost corners. The tools used during this step was a pencil. Step number 3. The magnets were glued to the foam board and in the indicated locations according to the horizontal and vertical lines. The tools used during this step was super glue. Step number 4. I placed the pencil, which I wrapped in tape, in the corresponding locations on the board and allowed it to the top half to fall in a hovering motion on top of the bottom. After this, I set up how the data charts were going to be organized. The tools used during this step was tape and a pencil. Step number 5. I began experimenting with the masses, measuring the zones, and recording the data. The average of the data I have taken is in the chart above. For child number 1, with a mass of 20 grams, the average zone of repulsion was 0.6 centimeters. For child number 2, with a 200-gram mass, the average length was up 0.4 centimeters. And for average number 3, with a 500-gram mass, the magnets in every occasion touched, not on the poles on the side, which will further be explained on a further slide. Here you can see the charts and how from day to day the magnet zones varied. The results. Throughout the experiment, I noticed that the masses got bigger and the pencils were beginning to bend towards the center. What I believe is that the cause that caused this was not the poles exactly, but it was the mass that you were adding on top. Because they were bending, the sides of the magnets were willing to touch each other, although the actual top was not. Every single time that I conducted this experiment, when placing the 500-gram mass on top, you would see that the magnets touch, although the poles never really did. Nor did the magnet shatter. The poles of the magnet remained non-touching, although the sides of the magnet did. Based on the research, the control group should have remained constant with the varying weights and would be dependent variable, which show us the resistance of the magnets through adding the mass up top, as you can see on Figure 1 and page 12 of previous turned-in assignments. Conclusion. Overall, through this experiment, I have learned that the sides of magnets are attracted to each other, although the poles will indeed never touch. This experiment, I have seen that through adding mass on top of the upper foam board will cause the pencils to bend towards the center, making it easier for the magnets to misalign and the sides to touch. Although it can easily be thought that the poles actually are touching, that is a misconception because the poles indeed are never touching, nor did the magnets break. In conclusion, magnets are stronger than mass because even though the 500-gram mass did make the magnets touch, the poles never did touch.